Hello, my name is Colón, and I will be presenting a Newtonian model of drag-based modeling for metachronal swimming. This project aims to develop a mathematical model for metachronal paddling and compare the results to the motion of a remotely operated vehicle, which uses the same locomotion strategy. Metachronal paddling is a widely used locomotion strategy used among free-swimming crustaceans, and Reynolds number ranges between 10 and 10,000. Examples of such swimming patterns can be observed in shrimps, like the mantis shrimp seen here, and the Antarctic krill from the previous slide. It is understood that metachronal paddling is an efficient locomotion strategy in these Reynolds number ranges, thus sparking an interest in bio-inspired robotics adopting said strategy. In order to control a robot, first a dynamic model must be created. This is exactly what Albin et al. Started to do by modeling the motion of a body using metachronal paddling, but they excluded the effects of a hinged knee, something that is believed to improve the paddling performance and this project aims to capture. The model derived in this project is based on a set of simplifying assumptions made to reduce the complexity of the problem. The first of these assumptions is that there is no hydrodynamic interactions between limbs. This simplification was made to reduce the degrees of freedom in the model, as including them would result in having to solve a fluid structure interaction problem. The second simplification made was the use of an idealized hinge motion profile given by a trapezoidal piecewise function. From previous observations, it had been identified that this profile will closely resemble the motions seen in the animals. And the final simplification was to constrain the motion to one dimension. In reality, the animal has 6 degrees of freedom, but for model testing and validation, the longitudinal axis was chosen to be studied. Below are the governing equations for the system. Equation 1 is the root angle motion profile, which is a sinusoidal profile, with A being the full stroke amplitude, F the stroke frequency, and phi the phase lag between paddles, as seen on the middle figure. Equation 2 is the knee motion profile given by a trapezoidal function with asymmetric rise and fall times. Equation 3 is the governing drag equation, where the indices I and j represent the number paddle and the part of the paddle respectively. The drag coefficient and paddle width were taken to be constant along the length of the paddle. Finally, equation 4 is a system of differential equations used to model the longitudinal motion, where F sub BD is the body drag, and the summations are summing the x component of the paddle drag forces for all paddles on top and bottom. To validate the mathematical model derived in this project, an ROV which uses metachronal paddling as its locomotion strategy was designed and built. The body consists of a 3D printed frame with an acrylic lid and paddles. Each paddle is independently actuated by a servo motor and controlled through a Raspberry Pi using a servo control board to set the position of each servo. The paddles are passively hinged with no control over the knee angle. To validate the model, the ROV was placed in a glycerin tank with a false wall to constrain the motion of the ROV. A camera was placed perpendicular to the tank and calibrated to know the mapping between pixels and position. Finally, the ROV was ran and recorded, from which the position and velocities were able to be calculated. Here are some videos recorded from our testing. The top row shows a positive correlation between stroke amplitude and the body velocity. The second row shows a positive correlation between the stroke frequency and the body velocity. After processing the videos and running the simulations with the same parameters, the following data was compiled. Here, each graph shows the position versus time for the different cases. It can be seen that the model and experiment do not agree, as the model both under and overestimates the displacement of the ROV. Yet the trends between stroke amplitude, frequency, and displacement are preserved. That is, in both the experiment and the model, as the stroke amplitude increased, so did the displacement, and the same for the stroke frequency and displacement. In conclusion, the model predictions do not agree with the experiments. Possible sources of error for this include the exclusion of fluid interactions, Reynolds number independence of the coefficient of drag, and the knee trajectories being independent from the hip trajectories. Future work in order to further refine the model include modeling the hip-knee dependence, collect data for more stroke parameters, and improving the paddling frequency response of the ROV. Thank you very much for your time, and if you have any questions, please feel free to email us. Thank you.